Okay, so I think we'll get started. I want to, first of all, thank everyone for attending. This is a bit of an unusual sort of seminar for us, but we've extended the invitation to a very large group across UHN, scientists. We've invited other administrators, some of our board members, and so on. And it concerns an area that I think is obviously of interest to everyone. We've got a terrific speaker today on this seminar, which is going to be a series where we're looking at some of the science and some of the thinking and the leading edge thinking around appropriate kinds of metrics to assess research excellence. Before we get started today, I do want to start by first acknowledging the land that UHN operates on. There's been a UHN hospital on this site since 1829. But long before that, Indigenous people were the stewards. And regardless of where we're all sitting today on this virtual call, we owe much to the people that call this land home. For thousands of years, it has been the traditional lands of the Huron-Wendat, the Seneca, and most recently the Mississauga of the Credit River. And today, the meeting place is still home to many Indigenous people from across Turtle Island. And we are grateful to have the opportunity to live and work here. We remember and honor the legacy of the peoples that have been here before us and all who have worked to make the promise of truth and reconciliation real. There is still much to do there, but I invite you all to join me to take a moment to reflect on the land that we're on today. So today we're launching our first, which, as I mentioned, will be a series of seminars that's dedicated to examining indicators of research impact and organizational excellence in all that has to mean for us here at UHN. And this is being done as part of the implementation of our strategic research plan that we launched back in 2019. We put together a working group to help us develop a set of indicators that would help measure our success and plan and against our strategic plan, and also track performance against our goals and benchmark against other individuals and organizations for research impact and organizational excellence. That team is here. They're responsible for the seminar series and for the invitation to our speaker today. It includes Heather Cole, Michael Hoffman, Tula Kalimaki, Azadeh Yadulahi, and our research analytics team. And they've been hard at work on this initiative for some time. We initially had a two-day seminar plan that was canceled as part of COVID, and we've regrouped and retooled into this virtual format. So with that in mind, we are really honored to have with us here today one of the influential experts in this area to help kick off the series, Dr. Jeremy Berg. And Dr. Berg is currently the Associate Senior Vice Chancellor for Science Strategy and Planning at the University of Pittsburgh, and also the President of the American Society of Biochemistry and Molecular Biology. Many of you will know Dr. Berg because he was formerly the Editor-in-Chief of Science in the Science family of journals, and also is the Director of the National Institute of General Medical Sciences at the NIH. And in this role, he has led multiple investigations into various research productivity metrics to help inform science policy at the NIH. And his talk today, I think, is going to present some of those perspectives on these experiences that help guide us in our thinking. So welcome, Jeremy. Thank you in advance for sharing these valuable insights today. And I turn the screen over to you. Thanks.
Well, thanks so much, Brad. It's a real pleasure to be able to give this talk. I wish I could have done it in person, but as with many things, it was disrupted by intervening events. So what I want to do is give you sort of three stories about different approaches to assessments in different contexts to illustrate some principles and highlight some potential metrics coming from sort of different parts of my career. So, one overarching principle, Peter Drucker, who is a big thinker about organizations and so on, said, if you can't measure it, you can't improve it. I would say the sort of flip side of that is don't just use what you can measure easily, but decide what you value and then figure out how to measure it. There's a real tyranny of metrics if you decide to measure something because it's easy, and then everybody will try to follow what they're being measured for, and that may not be the behavior that you're looking for. And one example would be, simply counting publications. If that's your metric, then everybody will publish many, many papers, many of which won't be worth reading. So the three case studies, and I'm going to try to go quickly so we have time for a conversation at the end. So a reviewer gender initiative, which took place when I was at Science. Secondly, sort of NIH funding comparison at US medical schools. And then finally, some sort of ongoing, sort of a progress report on ongoing work that I'm doing at the University of Pittsburgh. We have a relatively new dean after the previous dean stepped down after, believe it or not, 22 years of service. Didn't actually retire, but moved to a different position. So we're in the process of thinking about the right sorts of metrics to use at the School of Medicine and the other schools of the health sciences at Pitt. So the science gender question actually started before I got there, and that is the editors who were there were concerned about what were the genders of the authors who submitted to Science and what were the genders of the people who published in Science, to see whether the process of reviewing and selecting papers at Science was introducing bias on that pool of scientists. After that was done, and I'll show you a little bit about that, we started using the tools more generally to look at gender utilization by the editors, and looking at distributions as they varied from editor to editor. And then finally, a little bit about how these metrics can be used to modify behavior by the editors in this case. So when I got there, as I said, there was an ongoing activity looking at genders of authors and reviewers as well. The tool that was being used at the time, not to be disrespectful, were two very hardworking interns who spent the summer Googling people and trying to infer author and reviewer gender from web pages, from names, from pictures, and so on. This, as you might imagine, is quite accurate, but not very scalable. So they did thousands of people this way, but which was very useful for an initial analysis. But those numbers clearly weren't going to be useful if we wanted to look at trends over time and other sorts of things that would be of interest. The first next step in the process was collecting gender information voluntarily. So when you submit a paper to Science or the other journals, or if you agree to serve as a reviewer, then you're given the opportunity to complete a demographic information form, which includes gender, with the clear disclaimer that this will just be used for analysis and won't be used in any other way in the process. This is also quite accurate. The compliance and participation is limited, and there's certainly potential biases from people who agree to do this may not be representative of the entire pool. And the third approach, which I'll talk about in more detail, is using computational gender inference tools, which have some big advantages, but also some disadvantages. So these tools are based on comparisons of first names with databases with assigned genders. In the US, Social Security databases and other large databases with genders assigned to look at if your name is Jeremy, what's the probability that you're male? Is probably 98%, and so on. These are quite scalable. You can analyze very large data sets this way, but there are potential errors, uncertainties, and biases. So errors, a lot of the databases have been developed with Western European, American, Canadian sets of names. And when you get into a more international group of individuals, then there are errors and uncertainties associated with that, as well as biases, depending on how you use the tools, where they may be better at inferring male gender compared to female. And obviously these are better if you're looking at group analyses rather than an individual analysis. If you're really looking at individuals, then you need to be pretty sure that you're not getting very many gender assignments wrong. And so with the tools in place, it's always wise, and in any sort of science, really, just carefully validate your tools and refine them before you start doing wide-scale analyses. So the particular tool I used was a package called Gender, which is available for R. We use the original data set from the internet assigned genders for calibration and refinement, and then use the user supplied data set that I mentioned earlier for validation. And this is the first result, which was the original question, is, are acceptance rates for reports in science dependent on the gender of the corresponding author? And the uncertainties, the breadth of the things represent, the breadth of the symbols shown represent the uncertainty from the gender inference based on the analysis that was done. And I think the good news from the point of view of the editors at Science was there didn't seem to be much of a bias introduced by the reviewing and paper selection bias. There may be a small bias against females, but it was not huge, and that was unknown and was a concern prior to this analysis. I had a blog when I was at Science called Science Hound, and there's a reference here for a blog post which has a reasonable description of the analysis as well as the R code, so that you can play around with it if you want to. So then we turned to reviewer gender once the tool was developed, and looked at reviewer gender over time across the different areas that are covered by Science magazine. So the way the editorial team is divided at Science is basically into three groups. There's a life sciences group, which is pretty biomedical. There's a physical sciences group, and there's an other, which is social science, actually some aspects of life science, so ecology and geology in there as well. And as you might imagine, there are differences in the reviewer pool, presumably differences in the overall pool of scientists in these fields, in the different fields. And now we can look at trends over time, and what you can see is that there was a slight but significant increase in the fraction of female reviewers that took place sort of as this discussion started taking place at Science. And this is the other part of the slide, shows a histogram of the fraction of female reviewers across the different reviewers at Science. And you can see that there's a wide range, some of which relates to the field of science, and some of which just relates to editorial behavior. So to use, once we had this in hand, we started using this to try to help individual editors think about how they were doing. So as part of their annual performance evaluation, each editor was presented with the fraction of female reviewers they were using relative to the rest of the editors in their fields. So this graph is from one actually editor in the physical sciences who was actually pretty close to the median overall, and then moved up pretty substantially when these discussions started taking place and the information was shared. And in contrast, this is an editor in the life sciences, where there's overall a greater representation of women. wait a minute, this may be backwards. Anyway, the editor, no, this is right. And this particular editor tended to underutilize women beforehand, and her, actually it is a woman, behavior didn't change much when we started doing this. So this was there was an interesting editorial discussion with the lead editors about how this tool was actually useful at basically measuring sensitivity to change, willingness to change, and it correlated with general impressions of the editors from their supervisors. So let me move on to the next case study, which is comparison of funding levels at U.S. schools of medicine. The NIH ranking is one metric that deans and other university officials love to share, particularly if they're in the top 10. But as I'll show you, there's some problems with this, and then some questions about should all grant mechanisms be treated equally, and how should faculty size be taken into account. So this is the overall ranking from NIH from 2019. So Johns Hopkins is number 1 in overall funding, and you can read down the list. University of Pittsburgh is number 6. There's a fairly big group of institutions sort of between 3 through 7 or so. And there's been a lot of jockeying by deans trying to move up 1 or 2 slots in this position because of the perceived prestige about being higher on this list. The other, I mentioned, should all mechanisms be taken into account in addition to sort of individual investigator awards, which makes up the bulk of the funding. There are also some very large grant mechanisms which NIH uses, and they really come into two flavors. So there are some that are focused on the institution. So the biggest of these are the Clinical Translational Science Awards, which are typically on the order of $10 million in direct cost per institution. And these have a huge influence on the institution itself because they provide funding for infrastructure, which is hard to support otherwise, as well as generally supporting pilot grant programs and other things which help drive clinical and translational research from many, hundreds of investigators at the institution. There are other large grant mechanisms, which are, for example, coordinating centers for large multi-center clinical trials or data management centers. And those grants tend to be of great benefit to the NIH program and a great benefit to the national effort, but the impact on their local institution may not be that great. They certainly help employ some people there, but most of their interaction are with people outside the institution. So one way to measure the distribution of grant size is something that I sort of developed independently. It was when I was at NIH for looking at grant size distributions, and was talking to a social science friend who said, oh, economists have been using that for decades. It's called the Gini coefficient. And basically the idea is you rank the grants by grant size and then look at what cumulative percentage of funding is taken as you increase across the fraction across the ranking. So this is used primarily for looking at income inequality across populations. Here it's shown for Johns Hopkins, where the very large grants on the left side account for a substantial amount of funding, and then this, as you go across, you get to smaller and smaller grants. And the area of the red part, actually twice the area of the red part, is what the economists have called the Gini coefficient, and it happens to be 0.499 for Johns Hopkins. So here's that for across these same top 10 institutions, and what you can see is that some institutions like Duke, the Gini coefficient is higher, is 0.574, and that's completely consistent with anecdotal observations that Duke tends to have coordinating centers for large clinical trials and data centers and so on, whereas other institutions, and the lowest in this group is the University of Michigan, have a smaller percentage of those larger grant mechanisms and tend to be more dependent on individual grants, individual investigator scale grants. The other aspect of this, which has troubled me for a long time, and I'd actually never done this calculation before, is funding obviously scales with the size of the faculty. I experienced this actually when I started off my career at Johns Hopkins. We had a new department chair who came in, and he was bragging that he'd increased his NIH grant funding by threefold. And then I looked and discovered that he'd increased the size of his faculty by threefold. So it was a very different message. So here's what happens if you take those original funding data and divide by the number of faculty, which is taken from US News and World Report. So it's presumably reported by the institution, but there's a lot of nuance in which faculty you count in these numbers. The bottom line here is that there's a big difference because you look across institutions, with the most striking example, which again makes a lot of sense, is Stanford Medical School has a much larger than the median funding per faculty member, and that's consistent with the fact that that institution has some very, very strong basic science programs, in addition to some clinical departments as well, but a relatively small faculty compared to institutions like Pitt and Johns Hopkins and others where they have a larger clinical enterprise. So the last one is looking at publications metrics at the University of Pittsburgh, and the questions are, what should we do about publications numbers? How about citations? And then institutionally, looking at co-publication by faculty members in different departments as another metric of something that we certainly talk about a lot in terms of interdisciplinary science and so on, but how can we measure it this way? So a little bit of background about Pitt. There are 8 basic science departments, 2 interstitial departments, and by those I mean they're not really basic science departments, but they're not really clinical departments either in the same sense, and those are pathology and biomedical informatics. And then there are 21 clinical departments, some of which are quite large and have divisions. So here are the departments I mentioned, the 8 basic science departments, including computational and systems biology, where my faculty position is, the interstitial departments, and then here's the list of the clinical departments, again with the largest departments being medicine, surgery, and pediatrics, which are broken up into divisions which are all sort of approximately the same size as a basic science department. So in terms of looking at publications data, I started with data from Scopus from 2017, and that was chosen just because there was a sufficient time for reasonably robust citation data to be available. And searching Scopus for papers that were indexed with the University of Pittsburgh School of Medicine, with a department at the University of Pittsburgh School of Medicine from 2017, and there are 3,700 papers. And looking at the institutional affiliation, that's the author affiliation that's listed, 29 of these have only one department from the School of Medicine, whereas 970 have authors from more than one department. And then including the citations through December 2020. So there's a lot of data summarized on this slide. This shows the number of publications by department, both in the size of the circles, and then on the x-axis is the mean number of citations per paper, and on the y-axis is the median citation per paper. And then the color shows the percentage of publications that are just within the department as opposed to but involving more than one department. So a couple of points. First off, you can see at first blush, there's sort of as you would expect, a linear relationship between the mean and median citations, but with some outliers below that line. And those correspond to departments which have a much higher mean citations than median citation, which indicates that there are some very highly cited papers. So just to highlight one example, critical care medicine, which is the farthest off the simple relationship, has a much higher mean than median because they have in this year they had 3 or 4 very highly cited papers with hundreds of citations, and those come into two different categories. One is our results of large scale clinical trials that were published in this year, and the other papers that get a lot of citations are clinical guidelines, which are widely cited because they become the go-to reference for people using these guidelines in a wide range of studies. In terms of the percentage of publications in the department, you can see they range from very blue, which are departments that tend to publish with lots of other groups, some which are quite red, which means that they tend to publish only with authors within one department, and then a bunch in the middle. And I would argue that the middle is probably where the sweet spot is. You want a department that's strong enough that it's publishing things just within itself, but also collaborative enough that it's also publishing with a lot of other departments within the institution as well as outside the institution. Just a quick aside about journal impact factors. Hopefully I'm beating an already dead horse, but these are widely used. They're very useful for librarians in deciding what journals to look at, but for evaluating individual papers, that's not what they were intended for, and they're not really useful in that regard. So the advantage of a journal impact factor is they're available right away. The disadvantage is that they really aren't a good representation given how broad the distributions are at different journals. So this is a plot of the journal impact factor versus the number of citations for this data set. And you can see overall there are some real outliers of relatively modest cited papers in journals have a very high journal impact factor, and some very highly cited papers in journals that have more modest impact factors, and the overall correlation you can see is 0.36. So the last thing I want to talk about quickly is something that I've been working on, actually started at Science and I've been working on now, and that's using natural language processing as a way of inferring scientific areas to avoid having to do a lot of coding of individual papers or using departmental affiliation as a surrogate. So the idea basically is that papers, or at least abstracts of papers, is some of the raw product that's produced by scientists, and using the words that are present in the abstracts, one can get information about how closely related different papers are. So the idea is you use the distance between all pairs of abstracts using words in common, weighting words that are rare in the overall corpus of database. And again, this is done in R using Quantita, and then projecting this into 2 dimensions, or in this case, 2 dimensions, using principal component analysis. So this is what happens with those papers. If you do this, you get 2 principal components shown here. You get clusters. You see a bunch of outliers down, sort of isolated down toward the bottom of the graph, which were very striking. It turns out that those are papers largely to do with sleep, in fact, almost entirely. So sleep papers use words that are relatively rare in the database overall, like sleep and insomnia and so on. And there are enough of them because there's a lot of activity in the psychiatry department, particularly at Pitt, in that area, that they show up. To look at this, again, you can, looking at papers that have only a single department, this is now color-coded by department. So again, the sort of cyan purplish colors down toward the bottom are the psychiatry papers on sleep. And you can see that there is definitely some clustering of colors. You can see this more clearly by looking at now the average position for all papers by department, again, for papers that only have a single departmental affiliation within Pitt. And you can see this better on the next slide. So very gratifyingly, these these nicely segregate by departmental type. So on the left side, there are the 8 basic science departments shown in red. Toward the middle, there are the 2 cyan departments, which are the 2 interstitial departments, and the black represent the clinical departments, and the point down toward the bottom is psychiatry, again, because of these sleep papers. So with now these averages in hand, one can do analyses, for example, of looking at papers that are published by multiple departments. What does the distribution of distances on these, on the previous slide, look like across all of the papers? That in and of itself isn't that interesting, but what I was trying to get at is, can we measure the tendency to publish with departments that are in relatively disparate areas, far away scientifically from the departments in question. So the way I approached this was looking at distances between all pairs with co-published papers, calculating median distances for each department, and then comparing that with simulations if the co-published papers were randomly distributed. And the results are shown here. There's a relatively broad, more or less normal distribution in the center, where departments are sort of averaged. But then on the right side are departments which tend to publish with areas by this metric far away from their field. And gratifyingly, the alignment with my intuition was pretty good. So departments like computational and systems biology and microbiology and molecular genetics, some of the basic science departments, tend to collaborate with clinical departments on different projects. So they collaborate broadly on projects that are outside of their sort of core area. Whereas on the other end, there are departments that tend to be a bit more insular in how they publish. So to finish up, careful analysis can be applied to many different tools. Computational tools and large databases can be of considerable value in trying to develop and refine some of these metrics. Data sharing, as with the science editors, can help drive individual behavior once you've selected a metric that you value. Single parameters can be quite misleading, so always look at the whole distribution to make sure that you're not being fooled by one highly cited paper or one journal impact factor or something else. And then, again, this is just a progress, but I think scientific content can be assessed in an automated way that can help look at these sorts of things without doing vast amounts of coding before you start. So I will stop there, and thank you very much for the opportunity.